Here I'm happy to talk about good case and bad case latencies of unauthenticated Byzantine broadcasts. So this is joint work with Ittai Abraham and Ling. Let's start with the definition of Byzantine reliable broadcast, or BRB, which is the main problem we'll look at this talk. So in reliable broadcast, there is a sender that want to send the value and make all the honest parties agree on its value, even if some of the parties are Byzantine. So a reliable broadcast protocol should satisfy three properties. First, agreement, which means all the honest parties should agree or commit the same value. Second one is validity, which means when the sender is honest, all the honest parties should commit the sender's value. The last one is termination, which says if one honest party commits, then all the honest parties should commit as well. So Byzantine reliable broadcast has many applications, such as in Byzantine fault-tolerant replication, in blockchain, in secure multi-party computation, or in distributed cryptography. In this work, we are interested in the latency of Byzantine reliable broadcasts. Recall that by definition, when the sender of the reliable broadcast is Byzantine, then actually we don't require termination. Therefore, a natural notion of the latency for reliable broadcasts would be the so-called good case latency, which measures the latency for all the honest parties to commit under an honest sender. So the previous paper in Pozzo this year studies the authenticated Byzantine broadcast, which means broadcast protocols with signatures under different timing models. And in this paper, we studied the unauthenticated case, which means the protocol do not use any signature and is information theoretic. And in this talk, we'll mainly focus on reliable broadcasts under asynchrony, which means there is no bounded message delay. Since under asynchrony, the message delay is unbounded, a natural and standard notion is to use asynchronous rounds to measure the latency, which is defined to be the total running time of the protocol divided by the maximum message delay between any pair of honest parties. Then the good case latency of our asynchronous BRB can be defined to be R rounds if all the honest party can commit within our asynchronous rounds under an honest sender. Now let me show you some results for good case latency. Before that, there are two previous works on reliable broadcasts. The first one is the classic protocol by Braha, which has optimal resilience of 3F plus 1 and good case latency of 3 rounds. Then much later, Ibs and Reynal construct a reliable broadcast protocol with 2 rounds of good case latency by sacrificing the resilience to be 5F plus 1. Therefore, a natural question is, what would be the optimal good case latency under different resilience? And in this paper, we show that when there are 4F or more number of nodes, the tight bound for good case latency is 2 rounds. Otherwise, the tight bound of good case latency is 3 rounds. So in other words, the resilience of 4F nodes is the tight boundary that separates the good case latency of 2 rounds and 3 rounds. And we are able to extend and obtain the same result for Byzantine broadcasts under synchronous networks as well. Now let's start by describing the Braha's reliable broadcast as a warm-up. So this classic protocol requires 3F plus 1 nodes, which is optimal. The first step is the sender proposing its value to all the parties. Then when receiving from the sender for the first time, the party will send an echo message for the value to all the parties. Then when receiving N-F echo messages, the party will send the already message to all the parties. And then there is an amplification step, which says when a party receives F+1 ready messages, if it hasn't sent the ready message, it will send the message as well. Then finally, when receive N-F ready messages, the party will commit the value. So pictorially, this is what's happening. The sender first proposes, then every party will echoes the value and then send ready messages for the value. Therefore, when the sender is honest, all the honest parties will commit in 3 rounds. And the agreement of the protocol is guaranteed by the step when an honest party will send ready message only after receiving N-F echo messages. So here, the current intersection of these N-F echo messages ensures no two honest party will send different ready messages. And the ready message amplification step ensures termination, which means if an honest party commits, then there will be enough ready messages, and all the honest party will send the ready messages as well, and which ensures termination. Now let's describe our new protocol, which has optimal good case latency of 2 rounds and optimal resilience of 4F nodes. First, the sender sends value to all. When receiving from the first message from the sender, the parties can send the echo messages. Then when receiving N-F-1 echo messages from non-senders, which means any party except the sender, the party can commit the value immediately and send ready 1 and ready 2 messages to all. So this is basically a 2-round commit path in the good case. And here the threshold N-F-1 is because we only consider echo messages from non-senders. Then if it is not a good case and the node don't have so many echo messages, it will send ready 1 messages for the value if it receives N-2F echo messages from non-senders. Then the remaining step is similar to Braha's reliable broadcast, where the nodes will send ready 2 message when receive N-F-1 ready 1 message from non-senders. And the nodes will also amplify the ready 2 message after receiving F+1 ready 2 messages from non-senders. And finally, when the node receives N-F-1 ready 2 messages from non-senders, it can commit the value as well. So pictorially, this is what's happening. The first round is sender proposing to all. Then everyone echoes the sender's value. So if in the good case, then everyone already commits after these 2 rounds. Otherwise, the nodes will also exchange ready 1 messages and ready 2 messages. And another commit point is after 4 rounds, when they receive enough ready 2 messages. Now let's briefly argue the correctness of our protocol. First, for validity, if the sender is honest, it will send the same value to all the parties. Then all the honest party will send the same echo messages, which means they will receive enough echo messages from the non-senders and commit after 2 rounds. Next, we argue agreement property. If the sender is honest, then by validity, the agreement should hold. Otherwise, if the sender is Byzantine, then a key observation is there are only F-1 Byzantine nodes among the non-senders. So if we consider any two honest nodes that commits in round 2, if they commit different values, that means since each of them receive a -f-1 echo messages for that value, that means if we minus the f-1 Byzantine nodes among the non-senders, there will be at least 2 f honest nodes that sends the echo messages for two different values. However, there are only 3 f honest nodes, which means some honest nodes must equivocate, which is impossible. Therefore, by contradiction, we know that any two honest party that commits in round 2, they will commit the same value. So similarly, for the last commit step, by the current section of the ready messages, we know any two honest commit at round 4 will commit the same value as well. So the only remaining case is some honest commits in the round 2, while some other honest commit in the last step. Here, to argue the agreements, we'll show a lemma which says if an honest commits in commit value v in round 2, then no honest will send ready 1 or ready 2 messages for any other value v prime. Otherwise, suppose this happens, since one honest commit v in round 2, that means 2f honest nodes send echo for v. And if another honest send ready 1 message for v prime, that means you have received a -2f echo messages for v prime. So subtracting the Byzantine nodes, that means there are at least f+1 honest nodes that have echoed v prime. Since again there are only 3 f honest nodes, there must be 1 honest node that equivocated, which is impossible. Similarly, we can also show termination, but due to time limit, I'll leave it to the paper. As for the lower bounds, we show in our paper that any unauthenticated Byzantine reliable broadcast under less than 4f nodes must have a cookies latency of at least 3 rounds, even under synchrony. So this means our protocol described earlier has optimal resilience of 4f nodes. Another interesting latency measurement for reliable broadcasts is how fast the nodes can commit in the back case. Recall that the termination requires if one honest party commits, then all the honest parties should commit as well. So in the back case, the sender can make only some honest party commits in the fast pass, but the termination will require all the honest party to commit, maybe within some extra number of rounds. Therefore, we define the backcase latency to be the goodcase latency plus this extra number of rounds for all the honest party to commit once any honest party commit. As an example, the classic Braha's reliable broadcast has backcase latency of 4 rounds because in the good case, it can terminate in 3 rounds, and once one honest party commits, all the other honest party can commit within 1 round. Now let me show you our results for the backcase latency. First, we look at the backcase latency of the previous 2 reliable broadcast protocols. So the protocol by Braha, it has backcase latency of 4 rounds, as mentioned before, and the protocol by Ips and Reynal, it has 3 rounds of backcase latency. Therefore, our question is, what will be the optimal backcase latency under optimal goodcase latency, which is 2 rounds, and different resilience conditions. Here we give a complete picture by showing 2 impossibility results and 4 matching tight protocols. So the first impossibility result we have is for the general case when there are more than 1 faults, it's impossible to have a backcase latency of 2 rounds as well. So this is except the case when there are only 1 fault, where we show indeed there is a protocol which has optimal resilience of 4F nodes and optimal good case latency and bad case latency of 2 rounds. Then, since we cannot have bad case latency of 2 rounds in general, we ask if we can do 3 rounds. The second impossibility result says in general we cannot do that as well. So for the case when there are 3 or more faults, we'll need at least 5F minus 1 nodes in order to do that. Otherwise, if the number of nodes is less or equal than 5F minus 2, then we cannot have 2 rounds of good case latency and 3 rounds of bad case latency. So this is again except a special case when we have only 2 faults. So in this case, when F equal to 2, we can indeed achieve the optimal resilience of 4F nodes, meanwhile have good case latency of 2 rounds and bad case latency of 3 rounds. Otherwise, for the general case, when there are 3 or more faults, we either need to sacrifice the bad case latency or we need to sacrifice the resilience. So here we have 2 protocols. So the first protocol is the one I present you earlier, which has good case latency of 2 rounds and bad case latency of 4 rounds, and optimal resilience of 4F nodes. So the second protocol is a protocol that we improve upon the Eves and Reynolds protocol. So we keep the good case latency of 2 rounds and bad case latency of 3 rounds, but we improve the resilience to the optimal resilience of 5F minus 1 due to the impossibility result. Now let me summarize the results of our paper. We give a complete categorization of the good case and the bad case latency for Byzantine reliable broadcasts under asynchrony. So the first main result is we show we can achieve good case 2 rounds Byzantine reliable broadcasts if and only if there are 4F nodes. And the second main result we show is there exists inherent trade-offs between the bad case latency and the resilience. We show 2 impossibility results showing we cannot get everything optimal at the same time. And then we show 4 protocols that are optimal with respect to these impossibility results. So that's the end of my presentation. Thanks for listening, and my co-author will be happy to take any questions.
Okay, so hello everyone. Okay, so it's as we see, it is a work on finality in blockchain. So before starting, let's first really briefly recall what is a blockchain. So as the name says, it's a chain of blocks, and it's supposed to contain some immutable information. And when we implement it, what we have is that the blockchain is replicated among its participants. And so in this setting, the main problem is, okay, in the moment in which we want to append a new block to our blockchain, how do we keep the chain shape, knowing that some of the participants can be Byzantine. And so in what is done in the first blockchain that we know as Bitcoin is using the proof of work. So there is a crypto puzzle to solve, and the process that solves the crypto puzzle is allowed to append a new block to the chain and then to diffuse it to the others. So this is a way that we have to append blocks, but there is a problem. And the problem is that since here is the matter of solving a crypto puzzle, and even though we want that is hard as winning the lottery, we may have that for the same height, we have more than one process that is able to solve this crypto puzzle, and so to append two different blocks. And so in this scenario, what we have is the so-called fork. And it's something that we don't want because we say that we want to keep the chain shape. And so in this case, what do we do? On a certain point, eventually someone is able to append another block, and then so to diffuse it to the rest of the participant. And so then we apply what is known as the longest chain rule. And so we have that the longest chain is maintained, is selected as the main chain. And we here we are not really going to cut away the blue block, but we ignore the shortest path. And so we have what is called the fork resolution. And as we saw here, the first process somehow he changed his mind from the blue block to the red one. So this we can say that the blue block has been revoked. And this is the kind of behavior that we can observe in blockchains that provide eventual finality. And then in the case in which we want to avoid revocation, what we have to do, we have to use consensus. So the processes have to agree on the next block. And in that case, we have what is called the blockchains that provides immediate finality. So as soon as we have a block on the chain, the block stays there. And so now the question is, can be, okay, now we have those two kinds of finality, which one should we choose? So a way to think about that is, okay, let's think about the cap theorem. So what do we do in case of partitions? So the blockchains that provides probabilistic eventual finality are blockchains that favor availability over consistency. And so we have that blocks may be revoked from our chain, but have that the probability to be revoked decreases as the block sinks in the chain. And then on the other side, we said, okay, in case of partitions, we want we don't care about availability. We want to keep consistency. And then we need to pay the price of consensus, and we have a blockchain in which blocks are never revoked. So then the question is, what is in the middle between those two kind of properties? So the main goal of this work is really to explore as much as we can the different kind of finalities, the deterministic one that you can have in case of in this case, and to do that we introduced a concept, the concept of bounded revocation, where the idea is we put a bound on the number of blocks that given a chain can be revoked. And so as a result of the, among the different results that we have in the paper, we have that given this bound, depending on the values that we give to it, we can do reduction with consensus or eventual consensus. But we will see that a little bit more into details. But before going there, I need to introduce some formalization. In order to reason about those properties, we need to have some kind of object to consider. So we use the block tree that has been defined in another paper published in 2019. And essentially, the block tree, it's a tree of blocks. And this has two operations. The read just allows us to select a branch out of the tree. And the append operation that, given a block, allows us to append such block to the tree. Then, of course, this is not the only formalization that we have for the blockchain object. There is the first one of Garay, but it's really tied to the Bitcoin protocol, and it's protocol dependent. Then there is the one provided by Ittai, but it is a little bit too limited to the case in which we do not have forks. So back to our block tree, now that we have the object and the operations, which are the properties that we want to provide. So here we are going to define a block tree that provides event of finality. And we do that with 4 properties. So the first one is, you remember, we have 2 operations. So we are going to predicate on the result of the read operation. We have that for each chain that we read, the chain is valid. So the blocks that are in the chain are valid. So far so good. This is quite trivial and easy. Then we have the chain integrity. Still, if we read a block, this block was appended by someone. And then we have the eventual prefix. So the eventual prefix, it says, essentially, it can be a little bit hard to read the properties, but the idea is that given a read, which we have a block in a position I, for instance, we may change our mind a certain number of times, but the number of times in which we change our mind is bounded. And at a certain point, we read, for instance, a red block, and then we stick with the red block. Then, of course, we are pretty happy to agree on the fact that we are reading always the same block in the position I, but we don't want to stick there. We want to proceed. And so we need the evergreen tree properties that say that I read a chain with a certain number of blocks, and eventually the chain that I'm reading is increasing. And so that we have something like that. So this is the definition of the a block tree with eventual finality. Then, as we say, we introduce the notion of bounded revocation. What is the idea? The idea is we are still talking about the result of the read. So we have, for instance, we have a number n on the that is the number of blocks that we can remove from a chain that we read. What is the idea is that given a chain, we remove the last n blocks. In this case, n is equal to 3. And the remaining chain is a subset of the next chain that we read. Something like that. So this is the idea of the bounded revocation. And then we define some variation of this bounded revocation number. So we have the C bounded revocation, in which we impose a number on the a bound on the number of the blocks that we can remove, and this number is the same for all the histories. Then we have the bounded revocation, in which we have a bound, but this number may change from one history to the other, and then we have the eventual version of those properties. So to give a little bit an idea of what we are talking about. So for instance, if we have C-bounded revocation with C equal to 0, we can never go back. We can never revoke any block. So we just can have something like that in which we add blocks to the chain that we are reading. In the case in which we have C equal to 2, for instance, we can add block there in the middle. We just, how to say, we may change which are the last two blocks. So for instance, here, if we take R2, we remove the last two blocks, we have that the remaining chain is the prefix of the next one. And in case, instead of having the red block in the R3, we have a blue block, then we have a non-admissible round. And for the eventual case, we may have, for instance, in the case of C-bounded revocation with C equal to 0, we may change our mind for a certain time, and then from a certain time on, the property hold. And so those are the four properties that we just explained. So then the idea is, okay, we have those four properties. Now it's time to combine them with what we defined just so far, the eventual finality, the block tree with the eventual finality. And the result of that is other form of finality that we call deferred finality, because we may need to wait a little bit before finalize a block. Those are many, but the good news is that the last three, they are equivalent. So essentially, there are not so many deferred finality consistency. And so now that we have this finality, let's do some reduction. This is not a surprise, but if we take the C-bounded deferred finality, we have that it is equivalent to consensus. And if we take the other form of deferred finality, we have that is equivalent to eventual consensus. So just as recall, the eventual consensus problem is such that we have a sequence of consensus instances, and we may disagree for a certain number of consensus instances, but from a certain point on, all the consensus instances terminates in a good way. So everyone agrees. And then besides those reduction, an interesting main result that we have in this work is that you remember the longest chain rule that we said so far that is used in Bitcoin to decide what is the main chain when we have a fork. Well, interestingly, if you want to use this rule to build a solution for eventual finality in an asynchronous system, well, it's impossible. So we are not able to build a solution using this rule. The intuition behind that is quite simple. Just imagine that we have two processes. One is appending the red blocks, and one is appending the blue blocks. So here they are diverging, and at a certain point they will deliver, they will aware of the blocks of the other, and still depending on the delay, they may always remove one the blue block, one the red block, and so essentially they are never agreeing. The common prefix that they are sharing is never growing. And then another interesting point is, okay, so we talk about eventual prefix, and we cannot solve it in an asynchronous system if we use the longest chain rule. So how do we do? Well, We can solve it using another rule, and we can solve it with an unbounded number of processes. So, which means that we can have also an unbounded number of Byzantines. So, how do we do? Again, the intuition is quite simple. We assume that each process has a unique identifier that is in the domain of the natural number, and we allow all processes to append the blocks. So a process wants to append a block, he can do that. The only thing that we do is labeling each block with the identifier of the process. So this means that the blocks are ranked with the process identifier, so they have a lower bound that is given by 0. So this means that, for instance, in case of a fork here, if we use the longest chain rule, well, we should go for 4 and follow the path given by 4. But here, what we do, we pick 0. And we know that since we cannot have a block that has an identifier lower than 0, we know that we will stick with that block. So eventually we will grow in that direction. So this is a way to solve this problem with an unbounded number of processes. And then another interesting solution is that we discuss in the paper is how to solve eventual finality with the bounded revocation in an eventual synchronous system in the case in which we have half of Byzantine processes. So how can we do that? Again, just we will see only the intuition, but the idea is, okay, let's take an algorithm that, like Streamlit, for instance, that is designed to tolerate less than 1/3 of adversaries. And then we take this algorithm and we deploy it in a system which we have half of the processes that can be Byzantine. Well, of course, in this case, we can have forks because we are violating the assumption. But in this case, we have that the processes that are responsible for the fork, they are accountable because in this setting, I am not stressing that, but all the messages are signed, so we can account the processes that are misbehaving, and we can remove them from the system. So eventually, at a certain point, if we still, if we have forks, eventually we will remove sufficiently many processes from the system, so we go back to the system in which we have less than 1/3 of Byzantine, and we have no fork anymore. So here is the case in which we may have revocation for a certain amount of time, but eventually we will have no forks anymore, no revocation anymore. And so to conclude, I give you many definitions, but what we have here is that we define different kind of consistency criteria for blockchains. So we have the weakest one, that is the eventual finality, and then when we combine it with the deferred finality, with the bounded revocation, we have different forms of deferred finality. And in this context, we show that if we want eventual finality, we cannot use the longest chain rule as in Bitcoin, but we propose another way to solve the problem. And also we shown that in an asynchronous system, it's not possible to provide a non-bound on the number of blocks that can be revoked because of the equivalence with consensus. And finally, we show how to have eventual finality with half of the processes that can be Byzantine. And what we hope is that this can help in designing new blockchains consensus solution. And that's it. Thank you.
The last paper of this session is a paper with 7 authors: Shehar, Bano, Alberto, Sonnino, Andrey, Chursin, Dmitri, Perelman, Zekun, Avery, Ching, and Dahlia, Malkhi. And it's about Byzantine fault-tolerant system made robust.
Yes, so thank you very much. So this is a short overview of twins that are called BFT systems made robust. So this is joint work with a lot of people actually. So on the research side, it was Bano, me, and Dahlia. And on the engineering side, this would not have been possible without an extensive engineering effort that lasted many, many months from Andrey, Dmitri, Zekun, and Avery. So all the others work at Facebook, no EDM, depending which ones. So here is the general setting. I'm not spending a lot of time in introduction since the audience, but we assume a closed quorum system. The green machines that you see here are the harness nodes. And when we have the red one with a cross, then those are Byzantine nodes. So whatever happens in our quorum, we have at least 2/3 of good nodes, of the green ones. Good ones are not Byzantine and they would follow the protocol. So here is the story. So we have our system, these quorum systems. The user makes a transaction, sends the transactions to the user, to the quorum system. This transaction can do a lot of things. Typically, they would make some sort of payments. And once the system receives the transaction, it would run a very complex consensus protocol, because it may not seem complex to this audience, but in fact, they're still very complex protocols. Those would order the transaction, verify that it's good, honest, well-signed, well-formed, anything that's related with smart contracts, and finally, consider it terminated, add it to a blockchain, becomes highly available, and now it's considered settled. So these these consensus protocols are actually very complex. If we take the case of DMBFT, previously known as Libra BFT, so it's an example of production BFT systems. To be fair, it's an example of one of the rare BFT systems that actually run in production environments today. So this is a gigantic code base. It's more than 10,000 Git commits. It has been written by over 200 contributors, and it took years of development. So of course, it's not new, right? Software development has been here for a long time, and there have been the gigantic softwares before DMBFT. So that's not a novelty per se. What is actually a new problem that comes is the fact that now we have to deal with those Byzantine adversaries. And this is fairly new, right? Because then the engineering team came to us, so as the research team, and asked us, well, how do I write unit tests, integration tests with respect to a Byzantine adversary? By the way, what does it mean, a Byzantine adversary? What can it do? Can it equivocate? Can it do other things? And those were very practical and pragmatic questions, and we did not have a very good answer, in the sense that, well, you know, Byzantine adversary can do whatever it wants, but relax, right? The theory is backing it, right? But this only worked to a certain extent, because if the theory is right, it's always good, but there could be a ton of implementation problems in such a big code base. So that was a problem, and we realized there were no good solutions for it. So twins is our first attempt at a solution. So it's not perfect. It's, however, what we think is the best we have today. So it's not a formal verification tool. It's completely orthogonal. It takes a totally different path. We can see it as a pragmatic black box approach. It works in an extremely simple way. And I'm going to explain how at a very high level. So twins has two superpowers. The first one is that it creates multiple copies of the same node. So we take the code, the production code, the one that we would be running, and what we do with that, well, we instantiate our nodes, we instantiate as in a test environment, A, B, C, and D. The very good code base that we have, those we consider them being honest nodes. Then we take F and G, also nodes, that we want to make Byzantine. Well, now it's hard to tell what it means, but what twins does is, well, we'll create a twin, very exact symbol of the same node. So F will have a symbol called F prime, and G will have a symbol called G prime. So what these twins do? So these twins have the same cryptographic identity. So they have the same public key, that is the way that people name themselves in the space. And when they're elected as leader, well, of course, they would both propose, because the leader is selected through their identity, their cryptographic identity. But upon selecting a payload, every node, including twins, will generate a block with a random payload. Let's assume they have different clients that send them different transactions, or perhaps the same clients that send the same transactions, but ended up in a different order. So that's the first thing, making multiple nodes of F, multiple copies of F nodes. The second one is the network partitions. So once we put them in our network, on a round-per-round basis, we segregate them into network partitions. So on a round-to-round basis, because this changes every round. For instance, we have A, B, F, G that are in partition 1 along with E, and then in partition 2, the other nodes. So nodes of different partitions cannot communicate with each other, and nodes in the same partitions can. And you can have nodes that are like in an isolated partition so that they cannot talk to anybody, or nodes that are in both partitions, like node E, that can actually talk with everybody. That's the only node in this example that can talk with any other node. So if you take node A, it cannot communicate directly with node C. So a question that we often get, we don't have any sort of peer-to-peer network that runs on top of it that allows to vehiculate messages. This is just a pure protocol. This is how it currently runs. They have special dedicated channels with every other peer. Those channels are fairly complex, and they should be peer-to-peer links, basically. So yeah, so what does this help? So those two things help. So clearly, Byzantine adversary is a lot larger than that, not just having network partitions and twins copies. But here is the intuition behind twins, right? The intuition is that twins captures notable misbehaviors. Notable misbehaviors in the sense that most Byzantine attacks we know operates in those ways. So for instance, this equivocation is the first one. So when a node is selected as leader, and it happens that that node has a twin, well, then both symbols will think they're the leader, and they would generate a proposal with a different payload, as I said, and broadcast it to everybody. Yet everybody in the same network partition. So if the twins are in different network partitions, well, it may be the case that different nodes will receive different proposals without realizing it's a conflicting one. And amnesia can also be emulated by this twins behavior. So imagine the fact that forgetting that you already voted on a value. If we require replicas in those typical protocols like HotSoft, PBFT, Tendermint, they would all require votes, nodes to vote on a single proposal per round per node, things like that. Well, if you have both twins with the same cryptographic identity, well, they may vote here a different proposal, and they may both vote independently, because again, they may be in different network partitions. And the last one is loss of internal states. Most of those protocols would require node to keep some sort of locks over voted value to make sure that you don't rewind the chain. This happens in many quorum-based systems like HotStuff and most of its predecessors. Also, these with two different twins that do not share internal state with each other may cause locks to be lost from a system point of view. So here is a baseline case. I'm not going here in this presentation on more complex attacks because of time, but all of those are explained in the paper in very long details in the appendices of the paper if you're interested in a particular one. So the baseline case is, well, it should be obvious what happens if I have f+1 bad nodes. So if I have f+1 bad nodes, it should be absolutely trivial that I have a safety attack. So if twins cannot get that, well, it's a problem, right? It cannot get anything. But it's very trivial to get that. So it's fine. You just have A, D, and C in one partition, B, D prime, and C prime in another network partition. You run it that way. At some point, either C or D will be elected as leader. And when this happens, well, imagine C broadcasts a proposal to partition 1, C prime broadcasts a proposal with a different payload to partition 2. Well, both C and C prime will manage to get a quorum. 4 nodes, 3 nodes, C prime, D prime, and B would vote for the proposal of C prime, and A, D, and C would vote for the proposal of C. Do that long enough, you'll eventually get a 2-3 chain, depending on the protocol you run, and then we'll have a safety attack, a conflicting commit. So that's a trivial case. Obviously, if you have F+1 bad nodes, it's clear that we get this sort of behavior, right? But yeah, so twins is supposed to detect those attacks when you have only F bad nodes due to either protocol mistakes at the design level, but more importantly, implementation errors. So we have reinstantiated and expresses that twin scenario a number of known attacks in the literature. So the last decades, we've been building protocols, other people have been attacking our protocols, and we're playing that game for a while, and then a number of attacks are published on known protocols. And here are a few. The safety attack on ZZVAD, for instance, the liveness attack on FAB, tanning attacks on sync hot stuff, and some non-responsive attacks on linear leader reputations. I think that one was in the hot stuff paper at some point. So, so those are well-known attacks discovered well before twins, and we reinstantiated them as twin scenario by saying, what happens if we now run twins and try to recreate those attacks? How long would it take? You know, I mean, you would run twins with, as you may have imagined, with no coverage guarantees. And it turns out that the intuition was actually pretty correct, seems pretty correct at least, because in all those scenarios, twins found the attacks described in those papers within minutes, and without requiring a gigantic committee. We just run it with 4 to 7, sometimes 10 committees, nodes in the committee, and within minutes. So I mean, a few thousands, tens of thousands scenarios, network partitions, rounds. They managed to find the attacks and realize that there was a problem. So we also instantiated a new attack against one of the variants of two-chain hot stuff. At the time, there was only one. It was called fast hot stuff, which aimed to have a 2QC hot stuff version. The very first version was broken. I believe that now it has been fixed. And so we found and expressed as twins a new attack against that fast hot stuff version. Well, as of today, I think there are at least 3 2QC version of hot stuff. So in that particular case, when we just instantiated a twin, or we ran it in that way, we found the attack in 11 rounds. That's actually a few seconds, and we just committed for 4 nodes. So how did we implement that? So we have 2 main components for that. The first, we implemented what we call a scenario generator. So the scenario generator is pretty brutal. It goes ahead, produce all possible network partitions for a number of rounds, assign to each possible partition one of the possible leaders, and then it finds all the ways in which the leader partition pairs can be arranged on the R round that we decide to run the protocol on. After that, we've got a gigantic number of scenarios, and we filter the trivial ones. So what trivial means, it's difficult questions, we can chat about that later, but for instance, partition where every node is all the time isolated from every other node, clearly does not fall in the network model, so we would just filter them out. Yeah, this creates a gigantic amount of scenarios. So that's why it took some empiric evidence to realize that at least known attacks could be rediscovered within minutes. Yeah, because theoretically that's otherwise hard to tell. So the second component is the executor. So once we have all those scenarios and we know basically the game that we need to execute, we take our nodes, A, B, C are good ones, D is the bad one. So what we do, we create a twin, we duplicate it, we put it next to the other ones. We have some sort of network switch in between all those nodes, and the network switch now is aware of the directions given by the generator and makes decisions to execute the protocol. For instance, it may say, well, for the first few rounds, node A can only talk with node B, or I mean, node A can unidirectionally talk with node B, but B cannot reply, things like that, depending on what the scenario generator says. And so when you put everything together, we have the following pipeline. So typically the way these things would work is during your routine tests, that may happen daily or every nightly release, or potentially weekly or monthly. Well, what you do is you say you have a fixed amount of time that you will allocate for the twins running. So first you have the generator, which by the way can be run beforehand, creates the scenarios, give them to the executor, execute logs, and from the logs they go to persistent storage so that the script can detect if bad things happen. Then once the scenario generator is done, what we do is, if we have enough time left, we go back, we do more scenarios, and we start over. Otherwise, we consider the test terminated. And so this runs in production today. Actually, it has been running in production for a few months. It runs within the production code base of the MBFT. And yeah, so a lot of things are missing. So this is one of these papers that have a lot of related works. I mean, so future works. A coverage, for instance, we don't know what the coverage is. Once we run twins in that way, we don't really know if we're covering all Byzantine behaviors. We don't know if we're covering just a small fraction of them, or actually any of them some of the times, right? The second one is deterministic scenarios. So by the way of all those protocols are implemented in production, you never have a single core, single threaded implementation. So it turns out that the way you implement even consensus cores within those nodes is by having aggressively async and multi-threading. So it means that it's not because you feed to a node the same sequence of messages once that it will behave in the same way. So different reasons, time lock, times required to access storage, may create time variations in the async away pipeline, so that we don't really have deterministic scenarios. That's extremely annoying. And the other one is guarantees. So even if we had full coverage, namely we covered all the possible behavior that we could, because, you know, supercomputers allowed us to run all the scenarios that we could have generated, possibly all of them, right? For a gigantic number of nodes and a gigantic number of rounds. But even then, we would not know if we covered all the Byzantine attacks, because, you know, by the way of Byzantine adversaries defined, we don't really know. So those are like three very big future works. There are others, of course, but twins is a pragmatic approach to BFT testing. We believe the first of its kind, very different from most of the tools that are available out there. And it really needs a community effort to see if this is the direction that is viable, if this direction is a thing that we can improve. Can we provide coverage guarantees? Can we build it in a better way? Because, you know, twins, triplets, the idea of Sibyls and network partitions may not be sufficient. Right? So if you want the paper, it's there in the code, it's in the official DM code base. Thank you very much, and I think I'm right on time.